Okay, good morning everyone. I'm Abu Davi and Khairunisa Zulfamazi from Bandung Institute of Technology and our mentor Lucas Albert Suryana and Widwiaswati Rosita Dewi from Esri Indonesia. I'm about to present our paper that is Site Selection of Retail Shops based on Spatial Analysis and Machine Learning. This is the outlines of our presentation. The first is the background, the second is methodology. The third is the result containing planning phase and the evaluation phase, and the last one is the conclusion. The background of our research is that the market potential also brings challenge and competition for the retail industry in Indonesia, among which the first challenge is to choose the location that suits high market potential. As one of the basic issues in modern urban planning and city constructions, site selection comprehensively considers economic, environmental, and social factors which may often be conflicting in site selection. The appropriate determination of site selection will sufficiently use city resources and provide high efficiency for the public. An appropriate site selection strategy is thought to be an effective means to reduce costs and obtain high benefits in fields. The complex market potential and consumer characteristics have confused many retail business managers in site selection strategies. Therefore, the application of GIS or Geographic Information System for retail would be an innovation in business site selection for retail shops in solving socio-economic issues. The next is the problem statement. As we know, South Jakarta had been planned to become a satellite city as a support for major cities in the fixed vicinity. South Jakarta is also the most prosperous administrative city compared to the others, where in 2019, South Jakarta had the highest Human Development Index of all Jakarta's administrative cities, with an HDI of index of 84.75. Plus, most of the central business district is concentrated in Setiabudi, South Jakarta. This paper provides a novel method for selecting a new potential retail site in South Jakarta to support South Jakarta as a satellite city and CBD by implementing GIS with location analysis and machine learning. The next section is the methodology. We find out that the research on the commercial site selection issues reveals that the influence factors are often distinguished into several types as follows. One is the traffic factor. It is including type of the traffic network. The second is the number of POI, or point of interest facilities nearby, such as schools, hospitals, hotels, and etc. The third one is the competition factors, which are mainly the existing retail shops. And the last one is the quantity of active consumers who participate in business activities. Among the complex factors, the distribution of consumer groups, traffic networks, and POIs could be the main influence factors. This research has been divided into two main phases. The first phase is the planning phase. This phase determines the right hexagon area to find the optimal site selection for building retail. And the second phase is the evaluation phase, that is determine the optimal site selection for building new retail stores that have the same characteristics as the existing retail. We go to the first phase, that is planning phase. In this phase, we added the geometric figures in spatial analysis to collect point data into regular data. In the research, hexagon is used because it reduces sampling bias due to edge effects of the grid shape. This is related to the low perimeter to area ratio of the shape of the hexagon. Next, we generate the hexagonal grid using the ArcGIS Generate Tessellation tool in the range of 0.1 square kilometer to 1 square kilometer, and it was performed every 0.1 square kilometer. Then, we create the map of density of non-movable monuments with kernel density estimation. The hexagon polygon data that has been converted to point data using the feeder point tool was interpolated using simple kriging method. After that, we create 5 test layers composed of randomly generated 158 points created using Create Random Points tool, which corresponds with 10% of the complete set. To each particular point, the value of the chosen raster layer was assigned from the model map created using kernel density estimation and a map created using a simple kriging method. The 5 test layers were applied, averaging Pearson's correlation coefficients for 5 measurements, thus obtaining more reliable results. And finally, we do the scoring for each socioeconomic factors in 4 classes, and it would be summed up to be the final score and also be divided into 4 classes. The next phase is the evaluation phase. In this phase, we do the exponential smoothing algorithm to forecast revenue that represented sales in 2019 to 2020, based on the revenue in 2016 to 2018. Then, the 15 POI data are simplified into 3 data components using PCA or Principal Component Analysis. After that, we create 18 test random points using the Create Random Points tool. Then, we collect data on 3 data components that are close to the store in 15 minutes drive time area from the store and the 18 random points which were used as test data in the model we made. The characteristic of each store consists of the number of business places, public spaces, and open spaces, area of building footprints, area of residential quarters, value of traffic network, hexagon value, the value of the hexagon around, revenue, and the revenue growth will be trained in a model for testing random points. The sales estimate will be made to facilitate the preparation of income statement, cash flow, and balance sheet. In this case, we use the exponential smoothing algorithm to estimate the revenue that represents sales in 2019 to 2020. Then, growth revenue from 2016 to 2020 will be solved to determine the performance of each store. The purpose of this stage is to create a model to predict whether a place is suitable for use as a store or not, along with income and revenue growth per year predictions. However, in this study, there are many POI data sets and it is difficult to create models. So, previously, it is necessary to make fewer datasets using PCA. Datasets that have been classified into fewer information will be collected close to the store within 15 minutes driving time of the store. This was also done in 18 random points which were used as test data in the model that we made. Then, the characteristic data of each store consists of the number of each POI dataset that has been classified, the area of the building footprints, residential quarters area, network traffic value, hexagon values around revenue, and the revenue growth will be trained in models to test the random points. Then, the model will be tried at 18 random points as test data to test the success of the model. In this model, it will be determined whether the random location can be built as a new store location because it has the characteristics similar to the shop that has been built before. After that, The prediction of income and growth data can also be seen from each of the 18 location points in each of these random points. This is the result section. The kernel density tool is used to generate POI density maps in South Jakarta. The resulting image will be functioned as an image model from the reality where maps created using the general hexagon will be compared. KDE makes it possible to show spatial patterns accurately, but as shown in the materials and methods section, availability of point data may be limited. Then, the existing data point collection will be generalized to the resulting hexagonal grid series to find the optimal grid size. To the extent that the data can be generalized without a significant decrease in reliability. Polygon data in hexagons form is then converted to point data and then interpolated using a simple Kriging. The received tabular data was compared using the Pearson's correlation coefficient by comparing successive values of Pearson's correlation coefficient. One hexagon size was found, for which its value is the highest, 0.5 squared kilometer. The average value of the correlation coefficient for this hexagon size for all 5 test layers is 0.93866. A hexagon grid with an area of 0.5 square kilometer is shown in the figure. Then, we did a scoring for each socioeconomic factors in 4 classes and it would be summed up to be the final score and also be divided into 4 classes. The darker color indicates that the location is more optimal for a retail store to build. In this case, we use exponential smoothing algorithm to forecast revenue that represented sales in 2019 to 2020 based on the revenue in 2016 to 2018. The model that had been successfully run had an MAPE or mean average percentage error of 5.35%. Then, we have to make fewer datasets using PCA. From 15 POIs data can be simplified into 3 data components. The first component is classified as business, the second one is a public space, and the third one is the open space. Then, we collect data on business places, public spaces, open spaces, the area of building footprints, and the area of residential quarters that are close to the store in 15 minutes driving time area from the store. We did the same thing to 18 random points which were used as test data in the model we made. The characteristic of each store consists of the number of business places, public spaces, and open spaces, the area of building footprints, area of residential quarters, value of traffic network, hexagon value, the value of hexagon around, revenue, and the revenue growth will be trained in a model for testing random points. And the last section is the conclusion. This study is based on POI point data in South Jakarta and the results from a hexagonal grid of 0.5 square kilometer are the only results for this specific data. The methodology proposed in this paper provides universal application possibilities. Further research can be based on comparing different types of data using the methodology developed in this paper. Hexagonal lattice provides specific results, and comparisons of other geometric figures can also be the basis for further studies. Then, the model for finding additional store locations at a random point can be also applied universally because it has model accuracy of 75%. The model can be used to find the location of a random point that has the same characteristics as the previous store and is also predicted to provide good benefits for retailers. And that's all our presentation. Thank you.